The first speaker is Pavel Eichler with a talk on the direct numerical simulations of turbulent boundary layer fluid flow above rough surfaces using the lattice Boltzmann method. So, Pavel, you have, as usual, 15 minutes plus 5 minutes of the discussion and questions. So,
okay, thank you for the introduction. Good morning, everyone. So my name is Pavel Eichler, and I'm a PhD student at the Department of Mathematics at the Faculty of Nuclear Sciences and Physical Engineering of the Technical University in Prague. In this contribution, I would like to summarize our recent work based on the investigation of lattice Boltzmann method as a DNS solver for the turbulent fluid flow above rough surfaces. On this work, I have collaborated with Vladimir Fuka from the Charles University and with my supervisor Radek Fučík from the Technical University. So let's start. Okay, I will start this presentation with the motivation of our work. Then a numerical model will be briefly introduced and two benchmark tests will be presented. As I already said, the main aim is to investigate if lattice Boltzmann can produce reliable results in the problem of turbulent fluid flow above rough surfaces. First, we compare LBM with final difference method, which is commonly used in this type of problem. This comparison is content of the benchmark problem 1. Second, LBM results are compared with experimental measurements performed in the wind tunnel by Klára Jurčáková and Radka Kellnerová from the Czech Academy of Science. And again, the main question of this presentation is, can lattice Boltzmann be used as a DNS solver for the turbulent fluid flow above rough surfaces? Of course, DNS means that we don't use any turbulent models or laws of the wall in our model. So you know, DNS solvers need very fine mesh, especially in the boundary layer region, where the friction force is predominant role and cannot be neglected. Our work is based on the collaboration with our colleagues from the Czech Academy of Science to investigate the airflow in the experimental wind tunnel. And at the bottom of the wind tunnel, there is a plate with regularly distributed protrusions, which define the roughness of the wall. The airflow is measured with laser PIV in 2D plane and with hot wire anemometry, which produces one-dimensional data only. The main aim of this experiment is to investigate the generation and the evolution of the turbulent flow structures, which can have a different shape based on the value of the Reynolds number as illustrated in this figure. So that is our motivation. And now we can move on to our numerical method. Our numerical model is based on the classical lattice Boltzmann method. And because our simulation are 3D, we use D3Q27 microscopic velocity model. To achieve the sufficient stability, our numerical model, we use the cumulative collision operator introduced in 2015 by Martin Kaye. And of course, the macroscopic quantities such as the fluid density or the fluid velocity are recovered according to this formula. Our results were obtained using our C++ code with the support of CUDA and MPI for a parallel run on multiple GPUs. And now to the benchmark tests. The first test is inspired by the wind tunnel experiment shown in the previous slide. Our computational domain is a small part of the wind tunnel. Periodic boundary conditions are used in x1 and x3 direction, and the fluid is accelerated by this vector g. At the bottom wall, no slip boundary condition is prescribed using full-wave bounce-back boundary condition, and on the top wall, symmetric boundary condition is used. The kinematic viscosity is 1/70,000, so this is the kinematic viscosity of the air, and the computational domain is discretized with a regular mesh with the step h. At the bottom wall, there are small protrusions as in the wind tunnel. The dimensions of the protrusions are 1, 4, and 4 millimeter in the x1, x2, and x3 direction respectively. So the LBM results are compared with final difference method simulations based on the ELMM code. It's an abbreviation for the Extended Large Area Microscale Model, and it's developed by our colleague Vladimír Fuka. And because the smallest common scale is higher than the mesh resolution, our simulation can be called the DNS. For LBM simulation, the lattice had circa 62 million sites, and we need 14 gigabytes of GPU RAM. And thus we used 4 NVIDIA Tesla V100 cards. And now to the results. If we compare the vertical profile of the space and time average horizontal fluid velocity component, we see very nice agreement between finite difference method results and LBM results. If we compare the stress tensor component approximation U11, U12, and U22, U33, we see very nice agreement between ELM and LBM results. So the last pictures in this slide demonstrate the results of the turbine kinetic energy, and again, very nice agreement is observed. Now, we take a bigger part of the wind tunnel and again investigate the results. The only chance are that the computational domain is twice as large in each direction, and the value of the acceleration is smaller. And the computational mesh is finer. It's composed of 840 million lattice sites, and thus we use 8 NVIDIA V100 cards. Again, the results show very nice agreement between finite difference method and LBM results for the time and space averaged horizontal velocity component. And if we look at the stress tensor component, we see again very nice agreement, and both for the turbine kinetic energy. So to summarize our findings in this first benchmark problem, we can state that LBM produced similar results to finite difference method results. So, and let's move on to the second benchmark problem. This problem deals again with the fluid flow above and between buildings with HA, as illustrated in this picture. The computational domain presents again a small part of the wind tunnel, and LBM results are thus compared both with finite difference method results and with experimental results. Because we have only a small part of the wind tunnel, periodic boundary conditions are used in x1 direction, and thus the flow was again accelerated by this rolling force. No set boundary conditions are used at the walls in the x2 and x3 direction. So we have at the bottom and the top we have walls. Because the laser PIV measurement is performed in the middle of the wind tunnel, illustrated in this picture, the results are compared only in this plane. The red hatch rectangle represents the section where the experimental and simulated data are statistically compared. Although the Kolmogorov length scale is smaller than the mesh perimeter for our simulation, it is still a smaller multiple of the parameter h thus. It is common to call the simulation DNS2. So in our LBM simulation, we use this lattice, so it composed of 214 million points, and thus we used 4 GPU cards. And so to the results. I will start with a visual comparison of 2D data. If we compare the normalized time and space average horizontal velocity component, the results are similar. We see that there are only some maybe no differences or very small differences between experimental, finite difference, and LBM results. The results of the normalized vertical velocity component are similar again too, but small differences are observed, especially in these negative regions. You can see that the vortices are different. And maybe the biggest differences are in the stress tensor component approximation U11. However, I think that I can say that the results are still similar from from this visual comparison. So how far the simulated results are from the experiment can be seen in the 1D profiles better. The LBM results are compared with ELM results, it's a fine different method, and with the PIV and hot wire measurement. In this figure on the right-hand side, the data are, we can see the data in this dotted rectangle, it's zoomed. And it can be stated that the horizontal fluid velocity component is simulated well, especially in the region between the buildings. It means for x2 below 1. However, bigger differences are observed in the vertical velocity component. In the region between the buildings, LBM results are close to ELM results. But above the buildings, we see that the LBM results are closer to the external measurement, but farther from the final difference method results. And finally, if we look at the stress tensor component approximation and the turbulent kinetic energy approximation, we see very nice agreement between experimental and simulated data. So to compare the results in more details, some statistical metrics were used. We have used the fraction bias, normalized mean square error, L2 error, Pearson coefficient, factor 2, and the hit rate metric. And the best results are represented by the volt values. And if we see that for the horizontal velocity component, final difference method produces better results than LBM. But if we look at the vertical velocity component, LBM produces the best approximation of the vertical of this velocity. And finally, the stress tensor component is approximated by final difference method best, but it should be noted that in all these tables, the differences between the metrics are really small, because it's really hard to say which method is better. We can say both methods are really good. So finally, the scatter plots with the intervals from the hit rate metrics are presented. We can see that the low vertical velocities are a little bit underestimated by LBM. And the horizontal velocity component and the stress tensor component and the kinetic energy is approximated well according to this scatter plots. So to conclude our findings, the benchmark problem 1 investigated flow in the part of the wind tunnel with regularly distributed protrusion at the bottom wall, and LBM results were comparable to final different methods results. In the second benchmark problem, both numerical methods produce very nice agreement. Thus, to answer our question is yes, LBM can be used as a reliable DNS solver for the turbulent boundary layer flow. So our future work is to simulate the whole wind tunnel, not just a part. But for this simulation, we need a very fine mesh. Or approximations is that we should use something mesh which can be composed of 12 times 10 to the 9 lattice sites. It's really large, and for this we need something like 3 terabytes of GPU RAM. So unfortunately we don't have this hardware resources. Thus currently we work on the addition of mesh refinement techniques to our in-house code. So yes, we have some preliminary implementation, and now we just try to improve the efficiency. And with this refinement, we can simulate, of course, higher Reynolds number flow too. So presented results are summarized in this paper published this year. And that's all, and I thank you for attention.
Okay, thank you so much for this very nice presentation. If you have questions, we have time. Question, please raise your hand or write it on the chat. Okay. If there are no questions, let's thank again Pavel for this presentation, and let's skip to the next speaker. Thanks again, Pavel. And the next speaker, I think, is Hiroshi Otomo. If I don't go wrong, let me check on the program. Yes. Okay. Let me enable. Yes. Hi, Hiroshi. Can you hear me? I think so. I can't hear you actually because you have your microphone.
Yeah.
Okay, no.
No,
Yeah.
how about now?
You are very far actually.
Already?
Okay. No. Now I think it's
Now
better.
it's better? Okay. All right.
Yeah. Okay. Try first to share your screen, please.
Sure.
No. Okay. I can see it, and so I think the audience can see it as well. Okay. Okay, so first let me introduce you. The second speaker of this technical session is let me remember, Hiroshi Otomo. And the title of his talk is an under-resolved simulation approach for multi-component fluid flows in multi-case porous structures. Please, you can start, and you have 15 minutes plus 5 minutes of question and discussion.
Sure. So in this talk, we want to talk about multi-phase flow simulation, multi-component flow simulation in multi-scale geometry. So let's get started from one of the example image here. So this is a cross-section image of a typical carbonate rock, which is captured by micro CT scan. So this we just make the 3D volume geometry using this kind of a multiple cross-section images. And then let's try to assume the flow direction is just from our side towards this slide. So here, white color indicates 0% pore, which is solid. Black color indicates 100% pore, that means most of fluid. So if we, given this image, we construct the solid structure. So for example, here the white region is almost solid. But if we take carefully see this image, we see this kind of the gray region here. So that is because of under-resolved region with this scan method. So here's some of the list of scan methods. So there are a lot of scan methods here. So this image is captured by micro-CT, whose resolution is 2 micrometer per pixel. But if we see other the gray region using other scan method, for example, electron-based scanning microscope method here, we can resolve various structure inside this gray region, like here. So here's a question. Does this structure matter for the macroscopic flow? So often it's actually yes, because this microscopic structure contributes the connectivity of macroscopic pore. Also, because due to small scale structure, capillary pressure is usually high. And then also, depending on the structure, resistivity is varied. So that's why to resolve, to take into account this kind of microscopic structure to the macroscopic flow simulation is important. So next question is, should we make the simulation resolution finer as much as possible to resolve this kind of a microscopic structure? But if we take a look at this resolution difference between two scan methods, it's 20 times. No, it's yeah, 40 times different. So that's why if it's 3D fluid simulation, cube of 40 times computational cost is increased. That's too expensive. That's too much. So it's almost prohibited. So we have to treat some way for this microscopic structure. So here is our proposed workflow and the numerical model. For each this kind of grayscale region microscopic structure, we apply some numerical model whose inputs are some physical quantity. Physical quantity are absolute permeability, capillary pressure, relative permeability. So we pre-compute those physical quantity in this kind of typical microscopic structure. And then with that, we use such information as the input for the numerical model. Here, the absolute permeability is constructed based on the volumetric mass flow rate divided by cross-section. So it's indicated how easily flow goes through that system. So that's a kind of indicator. And the relative permeability is just component ratio for the permeability. Here, the capillary pressure indicates how much pressure is necessary for removing the water from that system, or to keep a certain water saturation level in that system, how much pressure is necessary. So that's capillary pressure's meaning. So here's what SW indicates the water saturation percentage. If SW equals 1, that means 100% water. SW equals 0 means no water. And the phi is, we usually indicate this phi as a porosity. That is a volume ratio, fluid volume ratio for the that computational volume. So phi equals 1 means fluid. Phi equals 0 means solid. Okay, so we try to pre-compute those quantity and then try to construct this kind of the resistance force, local resistance force. So first term is capillary force, and the second term reflects viscous force. So here the PC, K0, KR here, that's again pre-computed. And then depending on the local porosity value, depending on the local water percentage, this resistance force is defined. So that is a rough picture of our workflow and the numerical model. So once we simulate in this system, we also can store this physical quantity in this system and can apply this result to the even larger system. So that's a kind of rough idea here. So this workflow and numerical model is implemented based on the Shantian model, sometimes called the pseudo potential model. As our previous study, we keep using the filter collision operator as shown here. So here is the fourth term. So as a regular case, here is a intercomponent force. Now that in addition that we have the force from the porous medium model. Okay, the one benefit to using the lattice Boltzmann is that the natural extension of the wettability model. So for the wettability model, Shantian model, just extend for the wettability is we use this density term as the solid term. solid wall potential term. The similar way, if we referring the neighbor potential porous media box, neighbor porous media cell here, it's mean partially solid and partially fluid. So using that ratio, so ratio is a porosity actually. We assign the solid wall potential and the fluid wall potential. Then we define the total fluid potential in the porous media cell. So it's kind of natural extension. So next slide, I'm going to show some validation results. So first is a simple 2D channel case. So this system is left and right boundary is bounded by pressure boundary. The left one is mostly dominated by oil, and the right one is mostly dominated by water. And those pressure difference is controlled timely, as shown here. And then top and bottom wall bounded, bottom boundary are bounded by water wet solid wall. So, and then this is kind of the sandwich channel. So in the center region, there's no wall. So that's why porosity equal 1. So it's completely pore, whose channel height is 10. And the size region is occupied by porous media, whose porosity equal 0.3. So we try to input the capillary pressure for this porous media as 0.02 here. Because this is the test cases, we apply constant capillary pressure for the porous media region. On the other hand, according to Laplace law, for this porous media region, we can estimate the capillary force, like here, whose value is 0.005. So that's why if we keep reducing the pressure difference, like here, between these two stages, we expect the porous media is the water is embedded at first, and then these stages, pore side is embedded by water. So that's our expectation. And here's the input K0, KL, that's from a typical rock structure. So here's the result. So at this initial pressure difference stage, we don't see much water invasion. And if we reduce the pressure difference, then water is start embedding the porous media region at first. And then if we even reducing that, pore region is embedded. So that looks consistent with our expectation quantitatively. So next, we go into more detail, more complex system. This system is a cone-shaped hole is surrounded by porous media. So we try to compare two resolution cases. So here's a final resolution case. In this resolution 1 micrometer pixel, we can resolve all porous media structure like here. And then we don't need to use porous media model in this system. So we just directly simulate this system. And then if we make the resolution coarser by 4 times here, we miss the porous media structure here. It's displayed as a gray color. So that's why if we don't use the porous media model, that's completely impermeable because this hole is surrounded by solid. But if we use the porous, if we apply porous media model, we can just take into account this kind of porosity distribution in the porous media region, and then we can assign proper resistivity and capillary force on this porous media region surrounding the cone-shaped hole here. So the flow, the rough flow structure look like this, shown by arrow here. So here we compare three cases. Case A is we just simulate this fully resolving system without porous media model. And the case B is it is not necessary to simulate because it's completely impermeable system because surrounded by solid. And case C is based on this coarse resolution case, we apply porous media model. And then try to perform the K0 simulation. K0 means absolute permeability. So this is a single component flow simulation. And we assign some homogeneous body force over entire domain. And then second one is the PC simulation. As the previous cases, we control the pressure difference. And then this is a multi-component flow simulation. Okay, this is a pre-computed input PC K0 KR curve that is simulated in this system. In this fine system, the system size is very large. But once we can do that, we can use that input file data. So here is the K0 simulation. So here, firstly, we show the case A result, and then this is the velocity contour. So absolute permeability we capture is a 458, and then case B is because impermeability is 0. Case C is 486. So it looks comparable between two cases. Although case B, we completely missed this absolute permeability. And then if we compare the CPU, simulation time per CPU is 24 times saves. And next is this imbibition process simulation. So here is a PC curve. Y-axis indicates the pressure difference between top and bottom of the domain. And then X-axis shows the water saturation. So as we see, the red one is the case A fully dissolved, and then green one is the case C. It's a porous media model applied. So it looks consistent very well. Firstly, porous media is embedded, and then even reduce the pressure. Pore side is embedded. It looks consistent. Last case is a more complicated case. So we try to simulate 5 times different resolution with and without porous media model. And then we try to define case A, case B, case C as the previous case. So here is a single phase K0 absolute permeability simulation. We get this K0 value. So this case is even case B is permeable. So we get a reasonable permeability. But it looks like almost the same value we have. Thinking about the connectivity things, case B has least connectivity because we missed the all porous media information. So the connectivity relation looks like this. So qualitatively, it looks like follow this trend. Next is imbibition case. So that setting is almost the same as the previous case. So this PC curve, we show the red curve shows case A result, and then green one is case B, blue one is case C. It shows firstly, the porous media is embedded here. It looks almost consistent, and then later on, pore is embedded. That this we call the entry pressure. It looks consistent among 3 cases. And then we just show the water pattern, water invasion pattern at each stages, it looks consistent, pretty much. And then lastly, this is the residual oil pattern. So we usually see the residual oil pattern at the last stage, last imbibition stage here. So if we see case A and case C, we successfully get the biggest oil blob here, case A and case C, although we miss it in case B here. Also, second large blob also captured with the porous media model. So this case is, if we compare case A and case C, the computational cost is saved by 43 times. Okay, so this is just a preliminary result. We have already performed the relative permeability simulation.
Hiroshi, please proceed with the conclusion.
Okay, yeah, it's almost done, yes. Yeah, I think we have already captured a very consistent result between full resolved and unresolved result. Okay, so this is summary. So thank you so much.
Okay. Okay, thank you so much for this very nice presentation. We have time for one, I suppose, very quick question. If someone in the audience have a question. I actually have a question. Basically, your model aimed to coarse-grain the presence of under-resolved solid in your porous media by adding something like an ad hoc forcing term, right? Is it right, or am I missing something?
Right, and that force formulation, we need input. That input is pre-computed. Yeah.
Okay, my question is actually, how many free parameters do you have in your under-resolved simulation when you don't solve the whole porous medium?
We don't have, except for that input physical quantity, we don't have much free parameter. So here,
okay,
so this is almost exact force term. So PC come from
PC is a pressure, right?
Right, that's come from pre-computed simulation.
Is pre-computed by another by a resolved simulation.
Correct. Yes.
Okay, so basically the aim is to take a smaller portion of a whole porous medium, compute the capillary pressure from that simulation, and then go back into the under-resolved simulation by adding this forcing term, right?
Correct. Yes. Yeah.
Okay. I didn't get this point. Very nice. But this is similar to, other models like the Forkheimer-Brinkmann assumption in other. Yeah,
I think this viscous term is based on Brinkmann equation. Yes.
Okay.
I think these three quantity is full of this for three quantity. That is, I think, our novelty. I think. Yeah.
Okay, so thank you so much. Very nice presentation. Thanks. So I think we are done here, and I think we will resume in 20 minutes with the other three speakers. So see you here in 20 minutes, and thanks again to the...
Yeah, I think someone is asking in chat.
I cannot see the chat here actually because I have the...
Christoph?
Oh, yeah, you can answer. So thanks for a nice question. If I understand correctly, simulations you showed were run on CPUs, right?
Yes,
so
correct.
you intend to, yeah, okay. And do you intend to port them on GPUs? Yeah,
interesting question. We have not tried GPU yet. Yeah, in the future, yeah, we will try, yes.
Okay. Thank you so much again. And I think we can have our coffee break now. Thanks.
Okay, sure. Thank you.
Okay, I think we can start this second branch of the technical session. The next speaker is Jessica Padrone with a talk with the title Modeling Flood Events in Venice Lagoon with a cumulant lattice Boltzmann shallow water model. So you have 15 minutes plus 5 of question and discussion. Please go on whenever you're ready.
Okay, thanks for introducing me. I come from Italy and I'm in the first year of my PhD at the Niccolò Cusano University in Rome. I realized this preliminary work in progress with the collaboration of Professors Venturi and Di Francesco. The work I'm going to present aims to introduce an innovative model solution of the shallow water equation using the lattice Boltzmann method, which can be able to simulate large-scale phenomena like flooding events in presence of complex topography, and the alternative to computational fluid dynamics method traditionally employed for these aims. The ultimate goal is to performance the model in simulating acidic flood flows within domains of very complex geometry such as Venice Lagoon. So I'm going to show shallow water equation and lattice Boltzmann method and how lattice Boltzmann method can simulate a real flood event took place in Venice Lagoon, and then the model validation. Okay, the lattice Boltzmann method is based on the use of a particle distribution function representing the probability of finding particle with a given position and with a given velocity, and omega alpha is the collision operator and capital F is the external force. At the right side, we can see a shallow water equation derived from Navier-Stokes equation with the usual assumption of hydrostatic pressure and neglecting the effect of vertical acceleration, where h is the water depth and u is the velocity. Okay, in our work, we use this lattice pattern based on 9 direction and macroscopic variables. And the macroscopic variables can be recovered from first row ordered moments, depending on probability distribution functions. Viscosity is function of relaxation rate omega and the speed of sound that can be considered constant. Moreover, we use a multi-relaxation time model to improve stability and accuracy, and a cascading and cumulant methods which use as observable quantities central moments or cumulants. In both cumulants and cascaded, external force taken into account also in the transformation from central or cumulants to probability distribution functions. Boundary conditions play a critical role on accuracy, efficiency, and stability on the simulation because they can extremely affect simulation results. In our work, we use inlet or outlet boundary condition because due to computational limitations, the simulation domain has to be truncated and the boundary condition have to be set where physical problems don't have boundaries. The inlet and outlet boundary conditions are essentially inlets or outlets where the flow enters or leaves the computational domain. Okay, to modeling wet and dry fronts, we adopt a coupled procedure based on a threshold water depth and a fluid number limiter. In particular, nodes with the water depth h less than h lim as treated as dry nodes, and the velocity values are controlled, defining a maximum fluid number. To model flood events, we use an interchange routines based on the use of the open source QGIS platform, where we can prepare and verify the input data, such as topographic data, boundary condition, initial condition in pre-processing phase, and in post-processing phase, we can analyze the simulation results. The post-processing routines build flooding maps, very important for the flood risk evaluation, management, and mitigation. Okay, Venice Lagoon is situated in the northeast of the Adriatic Sea, and it is characterized by a complicated network of channels with maximum depth around 15 meters and shallow water flats. The three inlets of Lido, Malamocco, and Chioggia, situated at the eastern boundary of the lagoon, allow a water exchange between the sea and the lagoon. But what causes hydraulic risk in Venice Lagoon? First, its particular position. The lagoon is subjected to strong wind systems of northeasterly Bora and southeasterly Scirocco, which causes storm surge effects. Apart from the tidal and the wind-induced water level change, in the last 20 years, the city of Venice has had problem with the global sea level rise that together with the documented phenomena of subsidence, natural and human-induced by dredging artificial channels, has altered all the natural equilibrium of the lagoon, causing pollution, eutrophication, and coastal erosion. In order to verify the performance of the hydraulic model, we consider the extreme event took place in November 12, 2019, when a deep baric depression occurred, causing strong winds of Scirocco and Bora, and a maximum level of 187 centimeters was reached at Punta della Salute, as indicated in figure. The input data, such as the altimetric information, come from a digital terrain elevation model where we had existing buildings and the reconstruction of the internal and external bathymetry of the lagoon. Tide levels, tide data come from the recording of ISPRA tidal station every 10 minutes and is used to set initial condition and to validate the results. All of this is downloadable for free. Okay, so we reported simulation setting. We use two domain boxes, one bigger, including all the lagoon with a 50 meters grid spacing, where we have set as initial condition tide data of an offshore station situated at 50 meters far from the coast. In the second domain, with the 8 meter grid spacing, we zoom on Venice City and with Lido inlets, where we have set initial conditions. To validate models results, we use tide data of Punta della Salute station, located near the most famous Piazza San Marco. Okay, we have focused our attention on a time period around the maximum peak level reached at Punta della Salute, and we can see that with a 50 meter grid spacing, the results follow quite well the growing trend recorded by the station, and increasing the spatial resolution, the maximum is well captured, but the decreasing phase is only outlined at the initial segments. So we can say that the model is very flexible on multi-scale working, and we have we had an expected improvement, increasing the grid spacing. This is a verified light procedure, scalable and adaptable for local authorities to set up prevention and protection plans against hydraulic risk. This is an ongoing project, so the next step is investigating boundary condition to improve calculation performances and efficiency of the code, and to analyze tide levels in other areas of the lagoon without resolution. This is important to build flooding maps with the flood extension to prevent hydraulic risk with early warning system, possible because of the light computational cost, and to plan intervention to mitigate the hydraulic risk in Venice Lagoon area, considering the climate change next challenge, and to verify the effectiveness of this intervention and their interaction with the environment. Thanks for your attention.
Okay.
Thank you so much for your presentation. Are there any questions? Okay, Goncalo Antunes.
Hey.
Okay, yeah, you can.
So I'd like to ask, how exactly did you build the model for the Venice Lagoon? Was it already built, or did you manage to assemble it yourself out of pictures?
Sorry, can you repeat your question, please?
How did you assemble the model for the depth of the lagoon and all that? Is it already data that you have already available, or did you actually manage to assemble it somehow from collected pictures? Or
you write the code yourself to simulate the
code, yes, the code is developed by Venturi and Di Francesco, and we write the code in Python.
I think the question was most probably about the depth profile, the depth,
yes.
Let's say, topography. Do you also know this? Or
Yes,
just...
the topography. Yes, the topography was derived.
I think we have some problem with the connection.
Yeah.
Unfortunately. Jessica, can you hear us? No. Jessica? I think, okay, we lost the connection. Anyway, I think you can speak later. Okay, so I think we can skip to the next speaker. Let me take the program first because I don't remember. Okay, Kai, I think I have to allow you to share your screen.
Okay.
Okay, you are now a co-organizer.
Okay, thank you.
Please share your screen.
All right.
Perfect.
Can you see my screen now?
Yes, yes. Okay.
Thank you.
Let me present you first, but I have to take my...
Okay.
Okay, so the next speaker is Kai Key with a presentation entitled Investigation of the Exfoliation of Multilayer Graphene in Shear Flows, a lattice Boltzmann study. So I think you can start whenever you're ready.
Okay.
The floor is yours.
All right, thank you. Thank you for the introduction. So like now I'm currently a postdoc at CCOM EPFL. This work is done together with Professor Claudio Font from the University of Manchester and under the supervision of Professor Ignacio Pagnambaraga. So we are just trying study as shown in the movie, how the applied shear flow can exfoliate the multiple layer graphene. I think nowadays everybody knows that graphene is a monolayer nanostructure, which is composed of carbon atoms. It is arranged in the 2D honeycomb lattice, like here. It has some unprecedented properties, such like high transmittance, basically it's transparent, and high thermal conductivity, and extremely low resistivity, much lower than copper, and the high intrinsic strength, even though it's quite thin. With these properties, you can construct like solar cells or transparent touch screens or some energy storage devices. But the problem is the single layer graphene does not exist in nature. So you have to, the kind of like multiple layer structures are bounded by the van der Waals attractions among them and form this multiple layer structure, which is called graphite. And now the hottest topics in graphene study is to find an appropriate way to separate this multiple layers to produce the single layer graphene at the industry level. Obviously, we have to overcome this van der Waals attraction among the layers. So there are two ways. One way is apply the normal force to overcome the normal direction attraction. Another way is apply the lateral force, the shear force, to overcome the shear lateral direction. So the process to mechanically separate the graphene flakes is called exfoliation. And let's first look at the normal force case. The classic example is the micromechanical cleavage. So basically, you find a kind of sticky Scotch tape first, and then you stick this graphite onto it. then you close and then open, because the normal force acted by this sticky tape, then you can separate this graphite into smaller pieces. And then you repeat this process for many, many times. At the end, if you're lucky enough, you may just get some single layer graphene. And that's exactly what the 2010 Nobel Prize winner has done. The advantage is that you can get some high quality and a large area graphene flakes, but obviously it's quite labor intensive and definitely impossible to scale up to the industry level. And on the contrary, for the shear force case, there's recently an experiment. They made up a kind of equipment with a rotor and a stator. So the rotor can rotate to generate some rotating shear flow. So they put this device into the fluid, which is immersed with a huge amount of graphites. Once they turn on, the rotating shear flow can exfoliate the graphites into single layer graphenes like here and here. The advantage is that definitely has a much high exfoliation efficiency and is promising for the large scale production in industry. And one interesting problem we found is at very low shear rate, you can hardly produce any single layer graphene because this is a graphene concentration. And once you increase the shear rate to past a critical value, and then it can huge amountly produce this graphene. This shear rate is called critical shear rate. In their case, is 10 to the 4th per second. And now the question is, what is exactly the mechanism behind this? Then we try to answer this question by doing a cost-grained study with the lattice Boltzmann method. I definitely can skip these slides in this conference. I just want to mention we have the thermal noise and the force term here, and the simulation platform we use the Ludwig. The model is D3Q19. Okay, so to model the graphene, we use the subgrid particle, which basically an inertialess particle. The size is smaller than the lattice size. It is a stocklet to the fluid. Because it's inertialess, so its velocity is updated through its background flow velocity and the external force and the thermal noise. The question now is how do we get this continuous background flow velocity from this discontinued lattice? And we use interpolation technique. Basically, the contribution of the fluid nodes to the background flow velocity has to be modulated by this interpolating delta function, which has a dependence on the distance between the nodes and the particle. Similarly, the force act onto the nodes due to the particle is also modulated by this interpolating function. Okay, so we didn't model each of the carbon atoms directly. Instead, we used the coarse-grained way. So we group 4 of the atoms into one bead and then connect the bead by some effective potential. For example, we have the harmonic bond between 2 beads and the bending potential among 3 beads, which can just construct a honeycomb structure. And then the torsion potential, which can keep the whole structure in a plane. Afterwards, we apply the Lagrange attraction among all the beads and between different layers. Then we put a multiple layer graphite into the shear flow. This is all the parameters that we are using in the simulation. And the solution is water and the temperature is the room temperature. So we extend the graphite into infinity in the y direction by applying the period boundary condition, but we vary the length of the graphene in the x direction and change it from 1.8 to 6.8 nanometer. Okay, qualitatively, we can see that at weak shear, the graphene just tumbling, it cannot be exfoliated. But when the shear gets strong, it can be exfoliated. So the primary goal is to predict the critical shear rate gamma dot C here. Let's start with the simplest case. So we don't have the thermal fluctuation here first. And then we also turn off the the hydrodynamic coupling between the graphene and the fluid. So there's no force term act to the fluid. But the graphene can feel the background shear flow from the background from here. So the shear is basically like an external field to the graphene. So here you can see that when the graphene in the flow is tumbling, it can feel the flow, but it doesn't act to the fluid. So the fluid is intact. It's still like the shear flow. Okay, let's look at what is exactly the exfoliation condition. We put like a 2-layer graphene into the system, and then the frictional force due to the shear act on the first layer is calculated like here. And because it's static at the beginning, so velocity 0, and this background velocity is the shear rate times the distance, which is half of the interlayer distance. But initially cannot move because we have the attraction, lateral attraction from the second layer, this Lennard-Jones attraction. So only if this shear dragging is large enough to overcome this largest Lennard-Jones attraction, you can make you can separate these 2 layers. So this critical shear rate is calculated when these 2 forces are equal, and which is this result. Since we have many particles in each of the layer, so we can write this friction coefficient to be 6 pi at A times number of particles here. And then with some further simplification, you get a smaller f here. It's the Lennard-Jones attraction per particle. Okay, let's look at an example. Now we have the shear rate to be 60 per nanosecond, and we measure the Lennard-Jones attraction during this exfoliation process, and we found the maximum value is about 24 picnewton, which gives you the critical shear rate about 62 per nanosecond. We have done these measurements for many cases, like for different lengths of graphene and at different shear rates. The red dots are the exfoliated case, and the blue dots are the static case. The green dots are the estimated critical shear rate from the theory. So we have a good match with the simulation. Additionally, we see that this critical shear rate has no dependence on the length of the graphene. This is because for each of the length, the maximum Lennard-Jones attraction is identical. Then let's look at the multiple layer cases. Okay, so the 3-layer first. The frictional force acted onto the first layer is calculated like here. The only difference is that the height is the whole interlayer distance. Then the friction of the Lennard-Jones attraction by the second layer is like that, but we don't need to take into account this, from the third layer because the interlayer distance is large enough. So this is negligible. Sorry. Okay. Then the exfoliation can happen when this shear dragging is larger enough than this Lennard-Jones attraction, and the critical shear rate is this one. Okay, the example for the 40 of the shear rate, we found this maximum Lennard-Jones attraction is about 23 picnewton and gives the critical shear rate to be 30. And we have derived like the dependence of the critical shear rate on the number of layers. So for the odd number of layers, it is inversely proportional to n squared minus 1. For even number, it's inversely proportional to n squared. And the analytical prediction matches the simulation quite well. And we can see that when you have much more layers, it's easier actually to exfoliate because now the critical shear rate drops down. Let's now look at a more practical case. We still keep the thermal fluctuation off, but we turn on the coupling between the graphene and the fluid. Now, because they are they're coupled, so you can see the local flow field has been distorted by the graphene. Okay. The interesting thing is that the critical shear rate has been raised up like twice, compared with before it's 60, now it's 120. The conclusion is the hydrodynamic coupling hinders exfoliation. Then the question is why? So we took an example, like here, the length to be 3.8 nanometer and the shear rate to be 60 for each of the cases. By comparison, you can see that because of the coupling, the local flow field has been distorted by this tumbling of the graphite, and that makes locally the shear flow weaker. So you need to apply a stronger shear in order to provide enough shear dragging in order to separate the layers. Okay, let's look at an even more practical case. So we turn on the thermal fluctuation and temperature to be room temperature. And the hydrodynamic coupling, not only the hydrodynamic coupling distort the flow field, you can also see the thermal fluctuation has a strong perturbation to the field. Interestingly, the critical shear rate now dropped down to the 60 again, so the same as before. So the conclusion is the thermal fluctuation facilitates the exfoliation. If you do the comparison, this is because the thermal fluctuation caused each of the particle to wobble around their equilibrium position, and it's making it easier to cross the attraction barrier. Then you can just apply weaker shear to separate the graphene layers. Okay, to conclude, we have studied the graphene, using shear flow to exfoliate the multiple layer graphites to produce the graphene. The conclusion is that we found the exfoliation can happen when the shear dragging is larger enough than the maximum Lennard-Jones attraction between different layers. And we derived the dependence of the critical shear rate and on the number of layers. Another conclusion is the hydrodynamic coupling between the graphene and the fluids can hinder the exfoliation, but the thermal fluctuation can facilitate it. So I would like to thank European Union for the funding and the CSCS and CETAS for the support of the computation hours. And at last, I would like to thank you for your attention. I'm happy to take questions.
Thank you very much for this very, very nice presentation. Question.
So I see one question in the chat, actually.
In the chat, I cannot see, but okay, no, now I can see it. So okay. I'm sorry, the connection was weak. This is just okay. No, this is I think the previous speaker.
Yeah.
Are there any question here?
Hi, I have a question.
Hi.
Yeah.
When you talk about the first of all, thanks for the presentation. It was super nice.
Thank you. Thank you.
When you talk about the hydrodynamic coupling, which hydrodynamic coupling are you talking about? Which effect is the one you're capturing?
Yeah, a good question. So let's go back to the initially. So we initially modeled the graphene used the subgrid particles. Here is the equation motion of the particles, right? So this is the force act onto each particle, but at the same time, the particle can also feel the hydrodynamic force caused by the flow, by the fluid. So we apply this hydrodynamic force onto each fluid nodes. Initially, we have to apply to that. But the first trial is we turn off this coupling. So basically, we don't apply this force to the fluid nodes. The fluid cannot feel the force from the particle. But the second case, we turn on this force, just put the force act onto the fluid.
Is it clear now? Thank you.
Thank you.
There is a question from Marisol Paul. I think you can speak, Marisol. Yeah.
Hello.
Hi, Marisol.
Hello. Well, I'm sorry I was a little bit late, and my question is in the same line. So I understand then properly that when you have no hydrodynamic coupling, you are not seeing the lattice Boltzmann.
That's partially right. So if we don't hydrodynamic coupling, they can still feel the background flow field. This is just like active Brownian particle simulation.
Okay. Okay.
Yeah,
but,
it's external field.
Okay.
Yeah.
But then I mean, you have, I mean, it's a matter of completeness. You say hydrodynamics hinders exfoliation, thermal noise enhances it, or I don't know how you, what happens if you have, so you could have these Brownian motion simulation only with noise, would also be further increased? Or in combination of the thermal noise with the hydrodynamics? You see what I mean?
So you mean we don't have the fluid, just do the Brownian dynamic simulation for the stuff?
With noise, yes, because I understand that you do it.
Yeah, that's interesting. That's an interesting question. So that basically means we turn off the force coupling, but we turn on the noise term here.
Yeah, you have not thought about it.
Yeah, I never thought about that. That's an interesting question. Well, we could try.
I mean, one thing is, of course, that you can play with the method and you can switch things on and off. But on the other hand, it is interesting for me, the question, if it's something just combined with hydrodynamics, or if thermal noise itself has also that effect, or only in combination with hydrodynamics. So besides of just extending, so it can be from the physics point of view also an interesting question. I find it from the physics point of view an interesting question, and I think you have everything to just answer it.
I agree with you. Intuitively, I think the thermal fluctuation will facilitate the separation because again, like each of the particles, they will fluctuate around like or maybe I can just, they will wobble around, like just do this fluctuation. So you can sometimes the distance become larger, then the attraction, Lennard-Jones attraction become weaker in some sense. So you have relatively weak shear applied. So even though you don't have the hydrodynamic coupling between the fluid, as long as you have such a fluctuation, then occasionally you can make the attraction weaker. So I think you may still see this thermal effect there.
It would be faster than the athermal and no hydro, is what I mean.
Yes, I think so.
So that would be the comparison. So how it compares. Okay.
That's very interesting. Thank you.
Thank you.
I actually have a question, more a curiosity than a question. Do you think you are losing some measure information by modeling the water with a coarse grain, I mean, with a continuum approach instead of explicitly modeling the water as a molecule, with a fully molecular dynamics simulation? It's just a curious. I mean, I would like to have your idea about this.
Yeah, thank you. Actually, there's work has done before us. They are using the full molecular dynamic simulation. By this paper. But the thing is, they definitely for each fluid they explicitly simulate each of the fluid particle. But they don't let the fluid penetrate the graphite. So they have a repulsion potential, a repulsive potential just around the graphite. So the fluid just nearby. So the graphite can feel the flow field in some sense, but not hydrodynamically. There's no hydrodynamic interaction between each layer. So in their case. Okay. So yeah.
I'm thinking about this because I think that the gap between the two sheets is very, very, narrow, small. Perhaps it can be smaller than, I don't know, 3 molecules, on the vertical direction. So perhaps the continuum approximation may breaks, within in the gap within the two sheets. But anyway.
Yeah, actually, we did this test. We mapping from the real parameters to our lattice Boltzmann parameters. We change first this work here is we choose the bond length to be the same as the lattice length 1, so basically the identical. We choose the bond length to be twice larger or half smaller cases, so fine structure. We found the results are the same.
Okay. Thank you so much. Thank
you. No problem.
Very nice presentation.
Thank you very much.
So I think we can quickly skip to the next speaker, which is the last one, Goncalo Antunes. Let me just allow you to share your screen. Now I think you're you're able to share the screen.
Yes. Okay.
Okay. Let me first present you. Then the next speaker is Gonçalo Antunes with a presentation with the title "Advection-Induced Pumping and Mixing in Active Microchannels." So the stage is yours.
Thanks a lot. Thank you for being here. I would like to start by talking a bit about why we are interested in microchannels. In general, why are we interested in flows at the microscale? I have here two examples of how these flows can be useful. Consider here this microfluidic device. It's a series of microchannels, and these kind of devices often found in biomedical research. What this device can do is something quite neat. It can take a blood sample, and it can actually separate it into its constituents. So you end up having red blood cells here and T cells here. Then these purified samples can be used to do some further analysis, maybe some extra diagnostics. Another big class of examples of where microchannels are useful is in microsynthesis. So you see here a microchannel that takes in some flow of zinc oxide, and upon heating the substrate, one can form these structures here, these nanowires. Now, what's in common to all of these applications is a necessity to pump fluid in a controlled way at very small scales, namely scales ranging from the dozens of micrometers to the millimeter. So we need to develop micropumps in order to do all of these cool applications. Well, one thing we know about microchannels is that at such small scales, the ratio of surface to volume becomes quite large. So it suggests that one can use surface-based physics to achieve these kinds of efficient nanopumps or micropumps that we want to obtain. So enter diffusion osmosis. Consider a mixture of some fluid with some solid in it in contact with a wall. Let's say maybe here on the top we have the wall, and here at the bottom we have the fluid. Now we know there are microscopic interactions between the solid molecules and the wall. That means if we end up having more solid here than we do here, there will be a stronger interaction in this region of the mixture with the wall than in this region. This actually leads to a local pressure gradient along the wall, which drives flows along the wall. We may exploit these physics to generate a micropump in the following way. Consider a 3D microchannel, so a 3D hourglass shaped channel here, and we are going to coat the center of this channel with a catalytic material, meaning that the fluid that inhabits this cavity or this channel in contact with a catalytic surface actually undergoes a chemical reaction, and thus solute is created, or solute ends up as a product. This solute then diffuses around, and inside the bulk may suffer the inverse chemical reaction and thus disappear. Now, because we only coat the center in this catalytic material, we will naturally obtain more solid here than here, meaning we end up with gradients of solid along the wall, and therefore, because of diffusion osmosis, we end up with flows localized at the wall. Now, the important parameters that I'm going to be talking about is the extent of this catalytic coverage. So this ACOV, when this is 0, there is no catalytic material. When it is 1, the whole channel is catalytic. I will also be talking about this angle theta, which tells us how steep these walls are. So mathematically, we model the dynamics of the solid concentration using an advection diffusion equation. We have a source term here that is located on this catalytic wall, so on this surface. We have a sink term that is found everywhere in the channel. It is homogeneous. It models the inverse chemical reaction that destroys solutes. And here we have, very important, this advective term. This U is the velocity of the flow, which you obtain from the Navier-Stokes equation, the approximate solution of which we obtained from the Lattice-Boltzmann method. Now, I have told you that the only reason we can end up having flows is because there is an interaction between the solute and the wall. That means we actually have a force field that is being applied on the fluid. In a narrow region around the channel wall, this force field is non-zero. away from it, it is 0. So this force field is, these forces, they are proportional to the solid concentration, and this is how these two things couple. So we have a solver for the advection diffusion equation that gives us solid concentration. We plug it into the lattice-Boltzmann method, update the force field, obtain the flow velocity, plug it into the solver for the advection diffusion equation, and obtain a new solid concentration. So a very important number for the physics that I'm going to talk about is the Peclet number. This Peclet number relates or quantifies how important transport of solid via diffusion is compared to transport of solid via advection. When the Peclet number is very small, diffusion is the dominant transport mechanism, and we end up with steady states that look like this. So what you see here is flows along the wall going from a region of low solid concentration to region of high solid concentration. However, the overall force, the overall velocity field is actually left-right symmetric. So even though we have these local flows, we don't have an overall flow rate. There is no flow going from the left to the right. This system is not pumping. This is not so surprising as the channel itself is left-right symmetric. Now, a very different thing happens when we go to a regime in which Peclet is high and advection plays a role or is even dominant. We end up with steady states like this. I would like to call to your attention that there is a higher solid concentration here on the right than on the left. Now, diffusion is trying to equilibrate these two. However, the velocity field is actually bringing solid here from the left to here on the right. Now, eventually, these two can actually cancel out, or they become balanced, or they balance each other out. And the end result is a steady state that breaks left-right symmetry. And this steady state does pump. We do have a non-zero flow rate, and we are transporting fluid from the left to the right. So the message is, given a high enough Peclet number, a symmetric active channel can pump. So what happens when we go to even higher Peclet numbers? We end up with very interesting dynamics. We end up seeing this pulsating flow field that persists. We see it both in the transverse direction and in the radial direction. This greatly adds a functionality, which is we can also mix the fluid, not just pump it. So we have three classes of dynamics. One for low Peclet numbers, where we do not pump at all. We simply have these convection rolls. For intermediate Peclet numbers, we have steady pumping. For very high Peclet numbers, we actually see sustained oscillations in the flow rate, meaning our channel not only functions as a micro pump, it can actually also transmit a signal. Now we can actually control the properties of this signal. I'm going to show you now data for the period of oscillations associated to these oscillations, and this is what we get. So I'm showing you here results for constant Peclet, and I'm varying the catalytic coverage. So here, very little of the channel is coated in the catalyst, and here a lot of the channel is. And you see we can actually control the period of the oscillations. We can control the quantities of the signal we are transmitting. Now, why are these oscillations here to start with? Well, I would like to call to your attention that these periods, they are all smaller than this quantity here. In fact, this quantity is the relaxation time of the fluid. This is the time it takes for a perturbation to the velocity field to travel all across the channel. Meaning, the only reason we are seeing these oscillations is because the underlying dynamics occur faster than the time the channel needs to relax. Typical models consider these relaxation time to be zero. They consider relaxation to be infinite, the Stokes limit. When one does so, we completely lose out on all of the dynamics, on all of these oscillations. So these oscillations are tunable, and they are due to the finite relaxation time. So I was talking to you first about pumping. Let's see how the pumping strength actually depends on the various parameters. We can tune the flow rate, the pumping strength, by changing the Peclet number. You see here we have a critical Peclet. Then we have an increasing flow rate with Beclet. Interestingly enough, this dependence actually ends up being non-monotonic. It turns out that when we increase the Beclet even further, when we make advection even stronger, we can actually end up with a decreasing flow rate. Coincidentally, this actually coincides with the ushering or with the beginning of the oscillating regime. So these points here signal oscillating points, oscillating flow rates, and here steady pumping. We can also control the flow rate by changing the extent of this catalytic covering. When ACOV is 0, there is no pumping whatsoever because there is no activity whatsoever. Interestingly enough, when we increase the catalytic covering to very high levels, let's say, we also end up inhibiting the flow rate. Now, how can this be? We're actually making the channel more active. We're putting in more solids. How is the flow rate going down? Well, that is because what matters is not the total amount of solute. What matters is the magnitude of the solid gradient. When we increase the catalytic covering to include the whole channel, we actually decrease the solid gradients, therefore decreasing the flows and therefore decreasing the flow rate. We now keep Beclet constant, the catalytic covering constant, and instead change this angle theta. And we find first that flat channels cannot pump, and eventually that there is also a non-monotonic relation, and there is an upper, yes, hello, Marisol, you have raised your hand.
Yes, I didn't know if you would answer now, or can you hear me?
Yes, I can hear you.
I don't know if I'm missing something important. Are you putting an input flow? So where does your Beclet number, or saying it different, what is it breaking the symmetry of the problem?
So we have to break the symmetry with an initial perturbation. That's what sets the direction of the flow.
What is initial perturbation? Just an initial flow or an initial velocity, initial.
Yeah, so you see here we end up putting a bit more solid here on one side and on the other, and that's what drives the symmetry breaking.
Okay.
May we postpone the discussion?
Oh,
okay.
Sorry.
Okay.
So I wanted to tell you that there is not only can we not pump at flat channels, there is actually an upper angle for which we similarly stop having pumping. That is because as we make this angle very steep, we end up constricting the bottleneck, and that's end up constricting the flows and thus killing the mechanism that leads to the symmetry breaking. So the main message is, in order to have a symmetric active channel that pumps, we need both the chemical and the geometrical inhomogeneities. A channel that is fully coated in catalytic material will not pump, and a channel that is flat will also not pump. We developed an analytical model to capture this steady pumping. We consider an incompressible Newtonian fluid. We take a low Reynolds limit, we take the Stokes law, so we're not going to see any oscillations with this model. We just want to capture the pumping. We, instead of explicitly considering the interaction with the walls, we prescribe a slip velocity that is proportional to the gradient of solute at the wall. This slip velocity acts as a boundary condition to the Navier-Stokes equation, or to the Stokes equation, I should say. And we consider the advection diffusion equation for the solute. Now I'm going to very quickly run you through the main assumptions. First, we don't take a source at the surface. We're going to take a source that is located in the bulk. So we no longer produce solute here, we produce solute everywhere in the system. First, also, we consider that the source does not depend on the radial direction, instead only depending on the transverse direction or the longitudinal direction. We are going to limit ourselves to the case of a narrow channel where the length is much larger than its radius. And we're going to make this, we're going to use the fact that the typical potentials of interaction between the solid molecules and the wall are very short, and therefore it does not significantly directly impact the transport at the scales of the channel. And these two things together allow us to say that in the radial direction, the main mechanism of transport is actually diffusion, which, coupled with this assumption for the source, allows us to a very important simplification of the problem, which is to say that the solute density does not depend on the radial direction. It only depends on the longitudinal direction. Furthermore, we are going to assume shallow corrugation, meaning that the deviations of the channel height with respect to the average value are not very large. The fact that we used or that we are in a regime where the channel is narrow allows us to exploit the lubrication approximation. That means that the velocity in this direction varies much faster in the radial direction than in the longitudinal direction. That allows us to greatly simplify the Stokes equation and to obtain the velocity profile, which we get as a combination of a Poiseuille type flow due to local pressure drops with a plug flow. This is where, so to speak, the activity comes from. This is where the slip velocity plays a role. Now, the strategy is to cast our 3D equation or 3D advection diffusion equation and the 3D Stokes equation into a set of 1D effective equations. We do so by integrating the 3D equations over the cross section, and the end result is two equations where now the main quantities we're looking for is no longer rho, the solute density, but rather the integral of the solute density over the cross section. Also, we do not enter with the velocity directly, but rather the integral of the velocity over a cross section, meaning the flow rate. So here you can see this is the deviation of the perturbation, or the deviation of the channel height to its average value. If this is 0, the flow rate is 0 as well, so a flat channel can pump. Conversely, if the solute density also is constant, we similarly do not pump. I will spare you the algebra, but this system of equations actually exhibits a pumping transition, which we can obtain by a Fourier expansion of the source and the channel height. And we actually obtain an analytical condition for the pumping transition. The great thing about an equation like this is that given a certain set of experimental or chemical properties in which we see diffusion osmosis, we can actually obtain any channel geometry that gives us pumping, which is very useful because often these chemical properties are very, very hard to change. We compare this result with the simulations. So you see here varying covering fraction of the catalytic material and varying Peclet. The black crosses are the simulations for which we obtain no pumping. These hollow circles are the simulations for which you obtain steady pumping. And these filled in circles are the simulations for which you obtain oscillating pumping. And the prediction of this equation is this dotted line here. So despite all the simplifications we made, we obtain, without any fitting parameter, a quite good agreement with the simulations. To conclude the talk, I would like to mention that we can make symmetric active channels that pump and mix. We predict that this regime will be found at around lengths of 100 to 1,000 micrometer. We've shown that in order to get these symmetric channels to pump, we need both chemical and geometrical homogeneities together. We found that when we have a finite relaxation time and we take that into account, we can actually see a regime in which the flow field pulsates and the flow rate oscillates. And the frequency of these oscillations is actually tunable. And we predict them to be found in a range of frequencies of around 1 to 100 Hertz. Thank you.
Okay, thank you so much for this nice presentation. I think we have questions. Marisol, you want to make a question to Goncalo?
So the truth is that I didn't lower my hand, but I don't know if somebody else wants to ask. I would like to continue in the same line as before. So how do you think experimentally this chemical, so this initial perturbation can be included?
So there are, well, first of all, we know that there's going to be always thermal fluctuations. So eventually, even if you make a system that is mathematically symmetric, this pumping will appear. Mm-hmm. Besides that, one can also pick a preferred direction by starting with a little input flow. The other possibility is, so I've been talking to you always about a system that is coated in this catalytic material. What one can also do is simply use light activated catalysis. And then what one could do is simply, instead of doing this perfectly symmetric, just shift this a bit to the left, let the system attain a flow rate already to the left, then shift this back to the center.
I mean, that's what where I was going. I mean, you make emphasis in that this symmetric channel induces, which is interesting. But then my thing, since you need the other perturbation, is why not to make the channel a little bit asymmetric? I mean, we were. I mean, your work, by the way, is very nice. The talk was good, so it was very nice, and I didn't start there. So I like this work, but it's related to something that we did some time ago with asymmetric channels. So we didn't think about your nice idea of this perturbation and the large Peclet number. So that's perfectly okay. But we said, so you need an asymmetric channel, and then you can get this type of pumping. So that's.
So there are two things I would like to say. First of all, is that if one still has the symmetric channel, one actually has two modes of operation, which is for low Peclets, one has no pumping, but still this mixing. This mixing, by the way, at low Reynolds is also very hard to obtain. It is also very necessary. One needs to have a symmetric, one needs to have, usually for these chemical reactors, one wants a very homogeneous distribution of solids. So one could even turn the Peclet a little bit to go from the mixing to the pumping. The other thing is that since we're not inbuilt putting in the direction from the start, we can also switch the direction as much as we want. And we also have some preliminary simulations that tell us that in certain regimes, this symmetric channel can actually pump better than an asymmetric channel. That is because, let's say, if you take this channel here, if now you only consider the right half to be symmetric, you actually end up having less solid, so to speak. So there is a regime in which this symmetric channel can pump a bit better.
Okay, I will. That's very nice. It's convincing. And if you don't mind, I will send you these reference such that you can.
Yes, please. Thank you.
But thank you. Yeah.
We have time for other questions if someone has it. Okay, if not, we can conclude here this session. Thank you so much to all the speakers. All the presentations were very, very nice. I think we will resume at 3 p.m. Yeah, I don't have here the program, but yeah, with the plenary talk of Adriano Tribocchi. So thanks again to everyone.
2:20 I have, so 2:40 I have.
2:40. Perfect.
If the,
you are,
so 20.
Thank you. No, thank you so much. I don't have the program with me.
Yeah.